Okay, we can move on to the next paper, which is from one of our high-level TCOMS researchers, Law Yunqi. He's going to talk about the wave field prediction based on radar snapshots taking on a moving vessel.
That's how you use. Hi everyone, I'm Yunzi. And yeah, today I'm going to present my work on these wave field predictions based on the radar image taken on the moving vessels. So for an autonomous vessel, it is important for us to know and to predict how the vessel will behave or respond in the near future. And in order for us to know that, it is important that we need to know or predict the surrounding sea state or wave fields. And in this case, this is what we term as a short-term deterministic wave prediction, whereby we are need to predict the waveform itself, a phase resolved wave of a surrounding wave field of the surrounding wave field. And this is important because it helps and provides the information for the autonomous vessel in terms of the maneuvering planning and its pathway. And it also helps in terms of maybe optimization of the operational windows of a platform or vessels. So our work here is focused on to develop a framework which it takes in the measurement on the moving vessels, and then it tries to predict what will be the encounter wave faced by the vessels. And in this case, the measurement we are referring to a X-band radar. So an X-band radar is capable of capturing the snapshots of a wave field surrounding the vessels. So there are some commercial off-the-shelf products such as Ratel Vamos or these APS future waves, which are capable of doing this. So let me now move on to the framework. Okay, so our framework consists of 3 components. So starting from a wave field reconstructions, wave field propagations, as well as encounter wave predictions. And I'll go through them one by one. For the first component, which is a wave field reconstructions, the task for this particular component is to take in the measurements. In our case, will be X-band radar measurements. So take in these measurements, and then it process, and eventually the final outcome will be a reconstructed wave field surrounding the vessel, as well as its velocity potentials. So there are some methods available for these particular components. There is these 3-dimensional FFT methods, or there is these Jacobian free Newton-Carroll methods, and all of those, and including linear wave theory as well, that is capable to be fit into these components. So the output of this component, a reconstructed wave field, will then be passed as an input for the second component, which is these wave field propagations. Okay. So this propagation component is take in the reconstructed wave field and then try to propagate it in time for the futures. And for it to be practical and useful, this propagation method has to be faster than real time. And therefore, to some extent, it limits the choices of methods that we can have. So some of the choices would be linear wave theories, and maybe the higher order spectral methods, but with hardware accelerated, and maybe also the data-driven models. I mean, all these are again capable of fit inside these components. So this component, after it take in the reconstructed wave field, the output will be the predicted wave field in the futures surrounding the vessels. And this information will then be passed to a third component, which is the encounter wave predictions. So for this component, idea is that it knows what is the predicted wave field at our vessels, and then it anticipates where will the vessel be in terms of its pathway, and then based on that, it can evaluate the wave field at the positions where the vessel will be. So end up, this one will be predicting and give us a predicted encounter wave. And for this particular component, okay, for this encounter wave prediction components, it can be further extended such that, for instance, it take in the vessel motion prediction as well to be incorporated there. But for now, we will just stop at this encounter wave prediction at this stage. So at the current stage, we have implemented a baseline model for these frameworks by using linear wave theory. So for the first component, we are using the wave field reconstructions. We're using linear wave theory. So what it does is that it takes in the snapshots of radar images in the past. I'm using 3 snapshots in the past and use it to derive the derivative of surface elevation in time. And using this, I estimated the velocity potentials, and with that, I'm able to produce a reconstructed wave field. And for the second component, I'm using a linear wave theory as well, in which what I did is that, given the reconstructed wave field, I first Fourier transform it to a frequency domain, then phase shift it based on linear wave theory and linear dispersion, and then inverse Fourier transform it to obtain the predicted wave field. And then for the encounter wave predictions, what I did is that based on the predicted wave field, and then I assume that the vessel is following a certain path. So by that, I'm able to evaluate the predicted wave field at a certain locations. So in order to assess the performance of our baseline model, so we set up a synthetic scenario. So in this synthetic scenario, we have a shock crystal wave field generated by the higher order spectrum methods, 7 km by 7 km square. And then we assume that there is a vessel inside the wave field traveling in a turning circle pattern. And so we further assume that there's a radar mounted on the vessels which is capturing the wave field surrounding the vessel at every 2.5 seconds. The regions of this radar measurement is 1.6 km by 1.6 km. That means 800 meters from the range from the vessels. So then with just this radar information, we are trying to predict the encounter wave. So on your right, black line is the reference wave, meaning it is computed from the synthetic numerical measurements. Whereas the red line is the predictions of encounter wave using the baseline model that we developed. So at any point of time, we are only using the radar information in the past. So we never used anything before, anything after the current instance. So what you see is that for this particular C state, which is 12 seconds period, the result matched reasonably well. So we have also done the assessment for other periods as well. And basically what we found is that it is the accuracy related to its sampling rate, in the sense that if the underlying wave field period is comparable to the sampling rate, for instance, in our case, sampling rate is 2.5 seconds. And if you are talking about, say, a 5-second wave or 8-second wave, then the accuracy may drop because the period is just, the sampling rate is not high enough for those high frequency wave. So with this, let me just summarize what I've presented so far of our work. So up to here, our work is that we have developed a framework that is capable of streamlining from a measurements of a radar all the way to the encounter wave predictions, which consist of these 3 steps: reconstruction, wave field reconstructions, wave field propagations, as well as encounter wave predictions. Then the baseline model that we have developed based on linear wave theory, what we found is that the accuracy is quite strongly related to the sampling rate versus the underlying wave field. So then we also noticed that there's a limit in the prediction horizon because we have only 800 meters of range, and there's a limitation in terms of time we can predict in the futures. And in terms of future work, there will be so essentially is that to improve the methods for each of these components. For instance, the reconstruction components, what we can do is that we can implement data estimation methods, or we can also go in this data-driven model as well. And for the propagations, similarly that we can take in propagation with nonlinear effects, or as well as having a data-driven models which able to take in some form of nonlinearity. And then for the encounter wave, or rather this encounter wave part, we can be further extended to take in the vessel motion prediction as well. So yes, here ends my presentation. Thank you.
Thank you. Okay. No questions online, so do we have live questions here? Here we have one.
Brekke from NTNU in Norway. I just wonder, it wasn't entirely clear to me, what is the format of your radar measurements? Could you elaborate a bit on that?
Sorry?
What is it that you measure with the radar? Do you measure like
Oh,
the whole
surface
field?
elevations.
The surface
Meaning that-
elevation?
Yes, correct.
Okay, thank you.
Okay, more questions? Here we have one.
Rodan Denisik from iGauge. So how big is the area that is being monitored? You mentioned like 1.5 kilometers.
Oh, so a radar, the range of the radar, you mean? Yeah, so in this case, we are assuming a 800-meter range. So it consists still a 1.6 kilometer by 1.6 kilometer square in this case.
Okay, because on X-band radar, you've got like 10 miles or more. Like, can you take this information in calculations as well, or is it like too far?
Sorry?
So X-band radars, they go quite far.
Oh, so it depends on the radar specification. So there are some radar that we heard, that we saw is that from the specification, it mentioned that it can go up to 5 kilometers or what. And then there are some radar mentioned that they can only go up to 1 kilometer. So in this case, we are just taking the lowest in this case. But yeah, the radar range essentially, the range of the measurement essentially depends on the spec of the radar itself.
So then the application is, you're predicting the waves like in the next like 5 minutes, not like in 1 hour ahead, right?
So the prediction time horizon, indeed, yes. So it depends on two things. One is the range of the radar. The larger the range of the radar you have, obviously you can predict longer time horizons. Whereas also it depends on the wave period underlying. If the wave period underlying is very fast, that means this wave will be traveling very fast. So based on that particular radar range that you have, you can't predict the time after which the wave has passed through, in a sense. So yeah, so in our case, the one that we show, right, is roughly 1 minute plus or 2 minutes, given 800-meter range.
But I think it also depends on the height of the antenna, right? So that influences the range. But I think what would be the maximum time ahead that you think we could predict?
Maximum,
Maybe 10 minutes?
I computed once, but roughly 5 minutes. 5 minutes plus, that is for a very large range of radar measurements.
Thanks. Any more questions?
Hi, I'm Mayank. I'm from Center for Maritime Law. Just want to ask you, was there any parameter with real seafarers' estimation of the waves? And did you find any difference between your predictions and an actual human being predicting the wave changes? Or was that one of the considerations in your study?
Wave parameter, something like the statistical parameter, right? The significant wave period, all this, or?
Sorry?
So, I don't, so do you
Compared to a human, how does the radar prediction compare to like what a human would visually predict?
Oh, this one, no, I haven't taken into account yet though. That, yeah, how different between a human's visual wise versus a radar.
Okay, because I'm just trying to understand when you replace this prediction model, when you replace the seafarer on the bridge, does the model do a better job? If it does, that's the only benefit I see as being the replacement of the seafarer, right? So,
okay.
So I wanted to understand whether that was a consideration in the study.
With human, yeah, we don't really consider that yet. Meaning our idea is that we have radar that's helping us to capture the radar image, capture the surface elevation around, and with that information, how can it be processed such that we can understand or predict how the vessel will behave, or what kind of wave will be encountered by that vessel itself.
Maybe just a good idea to know for the study how far or how well in advance does a good seafarer or a capable seafarer predict the waves, right?
Yeah. Sure. Yeah.
Thank you.
Thank you.
I know of one case where the radar actually did better because there was a small amplitude swell, which was coming from a different direction. So it's kind of, to the eye, it's masked by the wind waves. You cannot pick it up with your eye, but actually had a big effect on the vessel roll motion. So if you wanted to, the radar could pick up the long period swell, whereas the visually it was hidden. So I think, but you're right. A good seafarer, he can feel in his bones what's going to happen next, and that's a difficult thing to enable.
Yeah, indeed.
Okay, more questions? Okay, I think we should move on. Thanks very much.
Okay, thank you.